An AI-generated post for your viewing pleasure. Conventional job shop scheduling models are crumbling under the weight of real-world uncertainty, but a new deep learning-powered approach is stepping up to the challenge. Wheatley, a cutting-edge algorithm that combines graph neural networks and deep reinforcement learning, is rewriting the rules of scheduling by learning to generate robust solutions that outshine traditional methods, even in the face of unpredictable task durations. In the high-stakes world of manufacturing and production, the ability to schedule jobs efficiently is the difference between a well-oiled machine and a factory in chaos. The job shop scheduling problem, JSSP, is a classic optimization challenge that has vexed researchers and practitioners for decades, as they strive to find the perfect sequence of tasks to minimize criteria like makespan and tardiness. But the real world is rarely so tidy. Machines break down, materials arrive late, and tasks take longer than expected, factors that can quickly turn a meticulously crafted schedule into a house of cards. Traditional JSSP models, with their deterministic assumptions, struggle to keep up with these uncertainties, leaving manufacturers vulnerable to costly disruptions. Enter Wheatley, a revolutionary new approach that harnesses the power of deep learning to master job shop scheduling under uncertainty. By modeling the JSSP as a Markov decision process and leveraging the representational prowess of graph neural networks, Wheatley learns to generate robust schedules that minimize the expected makespan, even when faced with unpredictable task durations. The results are nothing short of game-changing, as Wheatley outperforms conventional optimization-based solvers and priority dispatching rules, particularly on larger, more complex instances. At the heart of Wheatley is a novel combination of deep learning techniques that allow the algorithm to tackle the JSSP in a more holistic and adaptive way. By representing the scheduling problem as a graph, with nodes corresponding to tasks and edges capturing precedence and resource constraints, Wheatley can leverage the power of graph neural networks, GNNs, to extract meaningful features and relationships. This graph-based representation is then fed into a deep reinforcement learning (DRL) framework, where the agent learns to iteratively select tasks to schedule based on the current partial schedule. The key innovations in Wheatley's architecture include advancements in GNN design, such as the use of edge attributes and custom pooling operators, to enhance the model's ability to capture the intricate dependencies in the scheduling problem. Novel techniques for handling uncertainty and task durations, including the propagation of completion time distributions through the precedence graph and the integration of these uncertain parameters into the DRL training process. Careful engineering of the DRL components, including the action selection mechanism and the reward function, to ensure efficient and effective learning of robust scheduling policies. These technical contributions allow Wheatley to outperform traditional methods, particularly on larger and more complex JSSP instances with uncertain task durations. By learning to generate schedules that minimize the expected makespan rather than relying on deterministic assumptions, Wheatley demonstrates a remarkable ability to adapt to the realities of the manufacturing world. While previous research has explored the application of machine learning techniques to the JSSP, Wheatley represents a significant advancement in the field. Unlike earlier approaches that struggled with generalization and scalability, Wheatley's GNN-based representation and ERL framework allow it to tackle larger problem instances and adapt to a wider range of scenarios, including those with uncertain task duration. The study's introduction of the exceedance rate spectrum, RAs, as a visualization tool for evaluating the performance of scheduling algorithms under uncertainty is also a noteworthy contribution. By comparing the ability of Wheatley and traditional methods to accurately capture the impact of real-world traffic loads on bridge structures, the researchers have highlighted the limitations of current JSSP models and the need for more advanced techniques. Wheatley's success in outperforming traditional optimization-based solvers and priority dispatching rules, particularly on larger and more complex JSSP instances with uncertain task durations, underscores the potential of combining deep learning and reinforcement learning for tackling challenging combinatorial optimization problems. As manufacturers and production planners grapple with the realities of an increasingly volatile and unpredictable world, tools like Wheatley will become increasingly invaluable in maintaining efficiency, resilience, and profitability.